Hi, in this video we are going to talk about AVL trees or balanced binary search trees. So let's get started. So let's consider the situation when we want to construct a binary search tree from a sorted array. So we have numbers such as 1, 2, 3 and 4 and we want to construct our tree. So we have our first node, the 1, and then we want to insert the 2, and because the 2 is greater than 1, it's going to be the right child of 1. Then we want to insert 3, and the 3 is greater than the 1, 3 is greater than 2, and that's why it's going to be the right child of 2. Then we want to insert 4. 4 is greater than 1, 4 is greater than 2, it's greater than 3, so that's why it's going to be the right child of the node 3. And if we continue this process, we have a very large sorted array, we see that we will end up with a linked list. And if you may recall, if you want to find something or if you want to remove something from a linked list, it can be done in linear time complexity, which is worse than logarithmic time complexity. And if we remember, that's why binary search trees came to be, because we can insert and delete items in an efficient manner. So that's why it's better than linked list, and we want to maintain that property. So the running time of binary search tree operations depends on the height of the binary search tree. The height of the tree is approximately the number of layers it has. So in the first layer there's the root element, then the second layer consists of the left child and the right child of the root, and so on. So we should keep the tree balanced in order to get the best performance. What I mean the best performance? The best performance for inserting elements and retrieving elements and deleting elements. And this is why data structures came to be able to store, retrieve and delete items in an efficient manner when we have lots of items in it. So in an AVL tree, the heights of the two child subtrees of any node differ by at most 1. I'm going to talk a bit later about it. Another solution to the problem is the so-called red-black trees. There we do not bother about the height. We concerning colors, we assign a red or a black color to every node, and we make our constructing the trees and reconstructing the trees according to these colors. So AVL trees are faster than red-black trees because they are more rigidly balanced, but it needs more work, because on every insertion, in the previous chapter we have been talking about binary search trees and we inserting items in it. On every insertion in the AVL tree, we keep checking whether our tree is balanced or it has become unbalanced. And if it become unbalanced, we have to make rotations in order to rebalance it. In a red-black tree, we do not bossing around about reconstructing it so frequently, so that's why we have to do more work with AVL trees. But on the other hand, because of this more work, AVL trees are always balanced, and if it's always balanced, it means that the logarithmic time complexity is always met. So we can do every operations in logarithmic time complexity, while on the other hand, red-black trees, we do not boasting about reconstructing it every insertion, and that's why it is not rigidly balanced. And if it's not rigidly balanced, it means that the operations will take longer than logarithmic time complexity. So we have to make a bit more work with AVL trees, but it's much more faster than red-black trees. An operating system relies heavily on these data structures, so I think Windows prefers AVL trees. On the other hand, Ubuntu Linux prefers red-black trees. I think it's a matter of sympathy. I mean, to be honest, I prefer AVL trees. So yeah, and if you remember, the worst case scenarios for inserting, deleting and searching was linear for binary search trees, but here for balanced binary search trees such as the AVL tree, The average case complexities are logarithmic as well as the worst case time complexities. So that's why we keep rebalancing the tree in order to avoid linear time complexity, because logarithmic time complexity is much faster. Okay, so I've been talking about the height of a node. What is it? The height of the node is the length of the longest path from it to a leaf. I mean from the given node. So length of the height of the node is the length of the longest path from the given node to a leaf. And we can use recursion to calculate it, because the height of a given node is the maximum of the height of the left child and the height of the right child. And we increment it +1. So we get the maximum and we increment it +1. So the leaf nodes such as the 10, the 30 and the 50 has height value 0 because they are the leaf nodes. And we start from the bottom. We're considering that we have, for example, the 40 node. It has a left child 30 with height 0 and the right child 50 with a height 0. We get the maximum out of the 0, 0, it's going to be 0, and we increment it by 1. So that's why the height of the node 40 is going to be 1. And we keep iterating, we keep running this algorithm recursively for all of the nodes. And if we call it for the, because 10 is the leaf node, we assign 0 to its height. And the root node has a left child, 10, which has a height 0, and a right child, 40, which has a height 1. We calculate the maximum of these two numbers, and 1 is greater than 0, and we increment it by 1, and it will be 2. So that's why the height of the root node is 2. So when implementing this algorithm, we are going to have a class for each node, and in this node we will have a private field variable height, which is going to represent these height numbers. And I said earlier that whenever we have to make rotations when the height of the right child and the height of the left child, the difference between the two of them is greater than 1. The absolute value of this. So AVL algorithm uses height of nodes. We want the heights as small as possible. We came to the conclusion that if we make sure that these heights values are small, that our tree will be balanced, and that's our aim. So we store the height parameter, and if it gets high, we fix it with rotations. So the AVL tree requires the heights of left and right child of every node to differ at most +1 or -1. We can write it in a mathematical equation that the absolute value of the height of the left subtree minus height of the right subtree, we get the absolute value of it, and if it less than equals to 0, it means that our binary search tree is balanced. If it's not in this range, so if it's greater than 1, then we have to make rotations accordingly. So we can maintain this property, this AVL property, which means that our tree is balanced in logarithmic time complexity, which is quite fast. On the other hand, for example, when we want to make insertions, we have talked about insertions in the binary search tree video, and we just have to make a simple binary search tree insertion according to the keys. What are these keys? The keys are for example, if we talking about numbers, these are the numbers we assign to each node. So fix the AVL property on each insertion from the inserted node upward. So there may be several violations of AVL property from the inserted node after the root. So maybe there are situations when we have to make several rotations after each other. So we have to check them all, it's very important. So let me tell a few words about the rotations, and after that we are going to see a little illustration. Sometimes we have to make a right rotation, and we usually denote it with A, B and C, and the parent nodes are X and Y. If we make a right rotation on the Y, then the Y's left child, the X, is going to be the parent node in that situation. and the A and the B and the C subtrees are going to change accordingly. If we make left rotations on the X, on the right, so we make left rotations, and it is the same as the right rotation in the opposite direction. So if we rotate to right and then rotate it left, we end up at the same position we have been at the start. So we just have to update the references, which can be done in order 1, which is constant time complexity, very fast. And another important fact that the in-order traversal is remain the same, which means that on the left tree the in-order traversal is A, X, B, Y, C. The in-order traversal on the right tree is A, X, B, Y, C. So it doesn't change. And it's very important that these rotations are not going to change any property of the tree, such as the maximum item, the minimum item, the in-order traversal. Then why is it good to make rotations? Because we can make sure that our tree is going to be balanced. And why is it good that our tree is going to be balanced? Because all of the operations will have logarithmic time complexity. If we wouldn't bother about rotations, there may be lots of situations then we get worse time complexity than logarithmic. Most of the times we will end up in linear time complexity or near linear time complexity. So for example, we have a tree like this. The root is 32, it has a left subtree, a right subtree, and so on. This is a typical tree structure we have been familiar with. We want to insert 12. So we call our method recursively on the root, and we check whether the 12 we want to insert is greater or smaller than the root. We come to the conclusion that 12 is less than 32, so we go to the left subtree and call our method again recursively, as we've seen in the previous videos. The 12 is greater than 20, so we go to the right subtree. 12 is less than 19, so we go to the left. And the 12 is less than 16, so we insert another node here to the left. And as I said earlier, we make a single binary search tree insertion, but after this we have to check whether the AVL properties are met. So we have to calculate the height parameters. So let's calculate the height for each node. And it's very important that to be able to write an algorithm, a generic algorithm for calculating the height of each of these nodes, we consider the null pointers when a node have no left child, for example, or right child. For example, the node 19 has no right child, so we consider a node with height -1 to be consistent. For example, the node 41 doesn't have any children at all, so we consider its left children to be a node with height -1 and the right child with a node with height -1, and it's going to be consistent. So to be of height -1, yes. So because 12 is a root node, a leaf node, its value is going to be 0, so its height is equal to 0. Then we go upwards until we met the root node. That's what we've been talking about. So we visit its parent, which is 16. Because the 16 has a left child with height 0, and it doesn't have any right child, which means that it has a right child with height -1. And that's why it's important, because an algorithm doesn't know what it means that it doesn't have any right child. We have to specify that if it's a null pointer, we assign a -1, and because -1 is less than 0, if we recall how to calculate the height, for example, we come to the conclusion that we have to consider the height of the left child, the height of the right child. We get the maximum out of it and increment it by 1, and that's why it's going to be 1. Then we go to its parents and check whether it's okay or not. And it's a problem because the left child is height is -1, because we said sorry, not the left child, the right child, it's a typo. The left child height is +1 and the right child height is -1, because it doesn't have any right child. We assigned a -1 to it, and we come to the conclusion that the difference between 1 and -1 is greater than 1. So we have to make rotations, because that was the criteria, that our tree is okay. We don't have to make rotations until the heights of the the difference between the heights of the left and the right child, the right subtree, is less than or equal to 1. But in this situation it is 2, it is greater than 1. So we have to make rotations, and because this situation was doubly left heavy, we have to make right rotations. So the 16 will be the parent node, and the 12 will be its left node, and the 19 will be its right node. And we continue our algorithm. We calculate the height parameter for this 16, and it's going to be 2. We do the same for the rest of the tree, and we come to the conclusion that we doesn't have to make any new rotations, because the difference between the heights of the left and the right subtree is less than or equal to 1. So you can check it according to these numbers. So there are 4 types of imbalance situations, and that's why we have 4 types of rotations. We have the doubly left heavy situations when we have to make a right rotation. We have the situation when we have a left heavy and a right heavy situation. In that point we have to make a left and a right rotation. We have the situation when there's a imbalance situations that right heavy followed by a left heavy situation. Then we have to make both left and right rotations. And of course we have the situation when both of the situations are right heavy, and then we have to make a left rotation. So for example, we have a doubly left heavy situation, so we have to make a right rotation. We have to make a right rotation on the node 4, and it's going to solve us problem. Then then we have a situation like this. This is the double right heavy situation. Then we have to make a left rotation on the node 3. So here, sorry, I'm not sure whether I told it right, but in this situation we calculate the height parameters, and on the node 5 we come to the conclusion that it's unbalanced. So we have to make the right rotation on the node 5, and it's going to solve us problem. In this situation we have to make the left rotation on the node 3, and it's going to solve our problem and balance our tree. We have a situation like this, and it is the situation when we have a right heavy and then followed by a left heavy situation. In this case we have to make 2 rotations, right rotation on the 8 and the left rotation on the node 7. So yeah, and it's going to, so we make the, here we have to make the right rotation on the 8, and this is the situation when it's the doubly right heavy, so we have to make a left rotation on 7, and it's going to solve us problem. Okay, we have the opposite. We have a left heavy followed by a right heavy situation. Then we have to make a left rotation on the node 5 and right rotation on 7, and it's going to solve us problem. So for example, we have the problem we've been talking about in the first section of this video. We want to insert elements from a sorted list, so we insert 10. Then we insert 20, it's greater than 10, so it's going to be the right child of 10. Then we want to insert 30, it's greater than 10, it's greater than 20, so that's why it's going to be the right child of 20. And we have to make the rotation because of the unbalanced tree, so we have to call the left rotation on the root node, and it's going to balance our tree. Then we want to insert a 40. It's greater than 20, it's greater than 30, so it's going to be the right child of 30. We insert 50, it's greater than 20, it's greater than 30, it's greater than 40, so it's going to be the right child of 40. And we have to make rotations, we have to make a left rotation on 30, and it's going to make our tree balanced. So this is why it's very important to be able to write an algorithm that can rebalance our tree on every insertion and check whether if it needs to make this recalculation and reconstruction. And it's good because the logarithmic time complexities of our operations are maintained, and this is why it's very important. So thanks for watching.